Welcome to Electronic Materials. This video is the second part of Chapter 3. And now we are finally ready to discuss the hydrogenic atom. So what is hydrogenic? Why are we not just saying hydrogen? Hydrogenic means hydrogen similar atom, and so we say it can have a charge of Z in the nucleus but only one single electron. So it's not a very realistic case, but the solutions are the same for this case. So hydrogen is just Z equals 1. So essentially we are talking about the hydrogen atom, but the chapter is called hydrogenic. By now you should have a pretty good idea what to expect from the solutions of the hydrogenic atom. It's almost an electron in a finite potential 3D box, but of course there are some significant differences. So what stays the same? Well, we get discrete eigenenergies for energies that are smaller than the potential around the nucleus, because the electron is confined, right? So we will end up with something like this here. We will also get three quantum numbers from the solutions because we have three spatial dimensions now. What are the main differences to the three-dimensional finite potential box? Well, the most important one is that the potential V is not a step function, which goes from 0 to V0, but we have a Coulomb potential around a positive charge, and this Coulomb potential is a smooth function. And that's why we get an entirely different behavior when it comes to the spacing of the energy values that come out of the Schrodinger equation. What's also different here is that we will use spherical coordinates because we have a rotationally symmetrical potential. And so it's practical to use spherical coordinates. And the solutions of the Schrodinger equation then will have radial and spherical harmonic components, and they will have these remarkable shapes instead of just sine functions. Okay, let's see what we get as solutions for the Schrodinger equation in spherical coordinates. These here are the spherical coordinates I'm talking about. So we have the nucleus at the origin of the coordinate system, and then the spherical coordinates are the radial distance to a point in space, and then we have the polar angle, theta, and then we have the azimuthal angle phi. And with these three coordinates we can describe a point in space like we can do it in Cartesian coordinates in x, y, and z. The potential that the electron is in is a Coulomb potential around the positively charged nucleus. And that depends on the inverse of the distance r from the nucleus, so that radial distance. The hydrogen atom is Z equal 1, so we just have up here E squared, elementary charge squared. The solutions of this problem of the Schrodinger equation are wave functions that have a radial component and a spherical harmonic component. Since it is a three-dimensional problem, we get three quantum numbers. We have the principal quantum number n. That's very similar to the n that we encountered already in the potential wells. It essentially defines the distance from the nucleus. The other two quantum numbers, the orbital angular momentum quantum number and the magnetic quantum number, they determine where the electron is spatially around the nucleus. L goes from 0 to n minus 1, and L corresponds to S, P, D, F, and G, the nomenclature that we already learned with Bohr's shell model. And the magnetic quantum number ML goes from minus L to plus L in 1 steps. It's interesting to note that the radial component of the wave function depends on n and L, while the spherical harmonic component depends on L and ML. Let's have a look at the wave functions in spherical coordinates. This here gives the wave functions for n equals 1 and 2 and corresponding L and ML values. On the left you have the radial components and on the right the spherical harmonic components. Let's look first at the radial components. They are plotted down here. And so you see the 1s radial component is just an exponential function. For n equal 2, it gets a little bit more complicated because the factors in front of the exponential functions also depend on r, and so we get these functions here. Over here you see the probability density functions, and if you calculate the probability density for the 1s wave function, for the 1s radial component, you get a maximum here at the Bohr radius at 0.53 angstroms distance. We also see that the probability density for the 1s orbital is 0 at the origin, and that explains why atoms are not collapsing and the electrons remain on the ground state orbital. An interesting question is, why does the probability density function go to 0 while the radial wave function has its maximum here at the origin? This has to do with spherical coordinates. If we want to calculate the probability to find the electron in a shell of the thickness delta r, we need to calculate the volume of this shell, and the volume is calculated by calculating the area of the shell and multiplying it with this thickness. If we want to calculate the probability to find the electron in this shell, then we need to multiply the absolute square of the wave function with this volume. Since this volume goes to 0 when r goes to 0, the entire probability goes to 0 at r0, and that explains why the wave function approaches 0 at the nucleus. Let's have a look at the spherical harmonic components. For the s orbitals, these are just constants, but for the p orbitals we see that they depend on the angles, and that makes them look very interesting. Here you see 3D plots of the spherical harmonic components of the probability functions, and you see that the s orbitals don't depend at all on the angle, but p and d with L equal 1 and L equal 2, we have a much more complicated situation where the probabilities to find an electron strongly depend on the angular component. This also gives us a little bit an idea about the meaning of the angular momentum and magnetic quantum numbers. The angular momentum quantum number corresponds to the number of zero probability regions if we go 360 around the nucleus. If we go from P to D, you see that the number of regions with zero probability, the white areas here, they double. Right here we have 2 and here we have 4. That corresponds to having a higher L. The magnetic quantum number, on the other hand, corresponds to the orientation of the orbitals in space. Of course, this only has a meaning if there's an external field around the atom that gives a preference of one direction over another. If that's not the case, then these three orientations are, of course, completely equivalent, and the associated energy values would be degenerate. Let's have a look at the eigenenergies of the hydrogenic atom. The biggest difference relative to the potential wells is that their spacing becomes smaller as we approach the free electron continuum of states. In fact, the spacing becomes infinitely small at the transition to the continuum. That makes for a smooth transition between the discrete states that we have for the bonded energy states and the continuum of the free electron. Another difference is that the energies are now negative. They're called binding energies. The reason for this is clear, because these energies essentially correspond to the energy that we would need to give an electron that is on one of these discrete energy levels in order to make it a free electron. If we look at the formula of the eigenenergies, we see that they are proportional to 1 over n squared. And so it's clear if we go to high n levels or we let it go to infinity, then the energy becomes 0. So we're getting real close to the continuum of the free electron. And also here is the minus sign that accounts for this energy scale. This expression can be simplified if we calculate the energy of the ground state of the hydrogen for n equals 1. That yields 13.6 electron volts. And with that we can express this as z squared times the ionization energy divided by n squared. Okay, now let's have a look at the orbital angular momentum of electrons in the hydrogenic atom. If we draw the analogy to the classical mechanics case, the angular momentum L is just the radius of the rotating object times its momentum, so we have R times mv. In the quantum mechanical case, we calculate L by multiplying Planck's constant bar with the square root over L times L plus 1. And remember, L goes from 0 to n minus 1, and the L quantum numbers correspond to the subshells S, P, D, etc. So if the atom is in a space without any force field, let's think of it as being isolated in vacuum, then the L vector orientation has no influence on the eigenenergy of an electron state. In that context, all that counts for the orbital angular momentum is the length of the vector, which separates the energy states of the electron. In a classical sense, this would correspond to the angular momentum the electron has based on its velocity and its radius. It's interesting to have a quick look at the units of the orbital angular momentum. If you look up the units of Planck's constant, you will find that it is joule seconds. And if we look at the units of the classical case, we find for the radius meters and for the mass kilograms, and the velocity is meters divided by seconds. And so we have kilogram meter squared by second. So how do we get from here to joule seconds? Well, if you look at the units of energy in mechanics, you will find that the units of energy are the units of force times the distance, and that translates into m times a times the distance, and so we can say that the energy units are kilograms times meter divided by second squared times meters. And so it's obvious that this here is just joule seconds. So it's nice to see that we get the same units for the classical mechanics and the quantum mechanics case. I just told you that without an external field, the orientation of the orbital angular momentum vector L does not play a role, and we wouldn't see any difference in the energy levels of a state depending on where L is pointing. But as soon as we turn on an external field, we get a quantization of the z component of the L vector. And that brings into play the magnetic quantum number, which defines the values of Lz that are allowed. And so Lz is calculated by multiplying the magnetic quantum number with the Planck's constant bar. And remember, ml goes from minus L to plus L in one steps. So in this picture here, you see the allowed L orientations for a D state, right? When L is 2, so it goes from minus 2 through 0 to plus 2. So we get 5 orientations that are allowed of the L vector relative to the magnetic field vector. This here also means that the energy values of each of these states are different. And so the degeneracy of the L orientations, the energies of the L orientations, is no longer valid. This makes sense if you compare this with the classical case, where you can view the circular track of an electron as a current that goes in a circle. And such a current has a magnetic moment associated with it. And if the magnetic moment vector, which is perpendicular to the plane of rotation, if that's not aligned with the magnetic field, there's a torque that tries to align the trajectory of the electron into a plane that is perpendicular to the direction of the magnetic field. In other words, if the rotational plane is not perpendicular to the vector of the magnetic field, then there is additional energy in the rotation of the electron relative to the magnetic field. And this is similar to the case you saw over here. Depending on the orientation of the magnetic moment vector, we have different energy levels, if you will. of that electron rotation. Of course, here they are not quantized, so any orientation here would be allowed and possible. One more thing about the orbital angular momentum. There are selection rules when it comes to transitions between individual energy states. So if you think about an absorption process or an emission process where an electron jumps up or down on the energy scale, the selection rules specify that the orbital angular momentum needs to change by plus or minus 1, and that the magnetic quantum number needs to remain the same, or it can also change by plus minus 1. In an analogy to the classical case, you could envision that if you change the energy of a rotating object, you also change its angular momentum, because you get an increase or a reduction of the rotational frequency, or the radius changes of the rotating object. So it makes sense that the orbital angular momentum would change if the energy of the electron changes. So far we know that there are 3 quantum numbers, like we would expect it for a 3-dimensional problem, and these 3 quantum numbers, they define the state of the electron, and they tell us where to find it in space. It turns out that there are 2 more quantum numbers that are related to the electron spin, because the electron rotates around itself, and so it has an angular momentum. It turns out that there's only one spin quantum number, s equals 1/2, and with that quantum number we can calculate the electron spin. The electron spin is constant, it's just h bar times square root of 3 divided by 2. So the electron always rotates at the same angular momentum. Like the orbital angular momentum in a magnetic field, the spin angular momentum also gets quantized in the b direction. The component of the spin angular momentum in the direction of the magnetic field is calculated by multiplying the spin magnetic quantum number with h bar. The spin magnetic quantum number has only 2 values, plus and minus 1/2. So you see here what happens if we have an external magnetic field. The spin can be oriented either up or down, and this is how this is typically referred to. We say spin up for plus 1/2 and spin down for minus 1/2. Remember when I discussed the magnetic quantum number, I said it only becomes important if there is an external magnetic field. If there's no external magnetic field, the orbital angular momentum can point in any direction, and the energy state associated with it is always the same, so they are degenerate. Here with the electron spin, it is different, because the electron is always in a magnetic field which it creates itself. As it rotates around the nucleus, it generates a magnetic field similar to a circular current that goes around a current loop. That has the consequence that the electron spin is always quantized, even if there is no external field around the atom. Because of this, we can calculate a total angular momentum, which is a combination of L and S. The symbol for the total angular momentum is J, and J is calculated like all the other momenta by multiplying h bar with the square root out of the quantum number times quantum number plus 1. If we want to calculate the total angular momentum, there are 2 possibilities. We can either add the spin or subtract the spin. So we have J is L plus S and J is L minus S. You see that here in this nifty graph that I found. Here we have the original angular orbital momentum vector, and then we add the vector for the spin angular momentum, and the combined vector, that is J. If we put the atom into an external magnetic field, then again J here splits up into various quantum states that are quantized along the direction of the magnetic field. And so we get magnetic quantum numbers for the total angular momentum, mj. And mj goes from minus j to plus j, like all the magnetic quantum numbers. Since we have L plus s and L minus s, j is a fraction. Let's look at an example. So here for a p orbital, where j can be 1/2 or 3/2, we have the magnetic quantum numbers going from -3/2 to +3/2 if we use the j equals 3/2. If j is only 1/2, then of course we would have -1/2 +1/2 as the only two magnetic quantum numbers. I just told you that the electron spin is always in a magnetic field, and therefore one can see the quantization of the component in the magnetic field direction in experiments without applying an external magnetic field. Here's an example. Remember from chapter 1 when I introduced the Bohr shell model, I talked about the experiment to see the emission lines from hydrogen gas, and in this experiment one gets 4 visible lines: a red, blue-green, blue-violet, and violet line. So if you look at the red line, for example, at a high resolution, one can actually see that it is split into 2 lines. And the reason for that is that we have a transition from the 3s to the 2p orbital for that red line, and the 2p orbital has 2 total angular momentum states, 3/2 and 1/2, and therefore we can get 2 transitions. And the transition that goes into the lower of these 2 energy levels, that has a higher energy associated, and therefore we get a line that has a shorter wavelength. So that's the one on the left that is associated with the 1/2 transition, and the one on the right at a longer wavelength that corresponds to the smaller energy quantum that is liberated in the transition. So it's time to summarize what we know about the quantum numbers to define an electron state in a hydrogenic atom. We have 4 quantum numbers that are used to describe the electron state. The 5th one, the spin quantum number, is usually omitted because all the electrons have the same value, so it's not really interesting for distinguishing between the electron states in an atom. So let's go through those 4 that are important. The principal quantum number n goes from 0 to infinity. It basically defines the eigenenergy of an electron, and you can think of it as defining the distance of the electron from the nucleus. The orbital angular momentum quantum number L, which goes from 0 to n-1, it relates to the number of 0 probability nodes on a 360 turn around the origin. So the more complex these orbitals look like, the higher the orbital angular momentum quantum number. The magnetic quantum number ml, which goes from -L to +L in 1 steps, that relates to the spatial orientation of the orbitals, but of course that is only visible if there is an external potential that gives a preference to one of the directions in space. Finally, the spin magnetic quantum number ms, that has only 2 values, plus and minus 1/2, and that essentially relates to the orientation of the electron spin relative to the magnetic field generated by the electron itself. So in summary, these 4 quantum numbers define the state of an electron in an atom. If we have an atom with more than 1 electron, then the Pauli exclusion principle applies, which says that no 2 electrons in a given system can have the same 4 quantum numbers. That means that every electron must be at least different in 1 quantum number from all the other electrons in the system. So far, all we discussed in chapter 3 was about atoms with just 1 electron, hydrogenic atoms, just 1 electron. So the question is now, what happens if there are more than 1 electron like in most atoms? Well, the main difference is that if we look at the potential that 1 electron sees, in addition to the term that is related to the field around the nucleus, we have now a second term that is related to the potential that's coming from that second electron. The consequence is that the eigenenergies now also depend on the orbital angular momentum, and that comes from solving the Schrodinger equation with this additional potential term. The result of all this is that the eigenenergies are now splitting into sublevels. So in the hydrogenic atoms, we just had 1 energy level for each of the principal quantum numbers. Now we get several energy levels that correspond to the number of orbital angular momentum quantum numbers. So these states are no longer degenerate, but they have different energies, and that of course makes emission spectra and such much more exciting and complicated. When we go to more complex multi-electron atoms, the question arises how to sort the electrons into the electronic states. So in this figure, the electronic states are marked by these little squares here. So here we have for n equal 1, we have the s orbitals. Then for n equal 2, we have the s and p orbitals. And p orbitals have 3 boxes. And so the question is now, how do we put the electrons in for atoms that have more than 1 or 2 electrons? So here lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And each of them has 1 more electron. And so you see here how they get stacked in from the ground state up. You also see that we start out with spin up, and only when the states of one n and l level are filled with spin up, then we start filling in electrons with spin down. The rules that govern this process are essentially number 1, that electrons are filled in from the ground state up, so we start at the bottom at the lowest energy. This simply serves the purpose to lower the energy of the system as much as possible. That's how nature thinks. The second rule is Pauli's exclusion principle. I stated that already. Basically that means that each electron must have at least 1 quantum number different from all the other electrons in the system. And then we have a third rule, which is called Hund's rule. So Hund prescribes that electrons prefer to be next to each other with the same spin. And that means, and that's also again for lowering the energy of the system as much as possible, that means that electrons are stacked in with the spin in the same direction into L shells, and only when the L shell is completely full with electrons with the same spin, then we start filling in electrons with the opposite spin into each L shell. So in summary, we can say, first determine the orbitals from the Schrodinger equation, and then stack in the electrons. Start at the ground level, make sure that each electron has a different combination of the 4 quantum numbers, and observe Hund's rule, which prescribes that electrons need to be filled into a L shell first with the spin in the same direction, and only when all magnetic quantum number denoted L orbitals are full, then fill in the electrons at the opposite spin. And this brings us to the last part of chapter 3, stimulated emission and lasers. So now we understand how we get electronic states, and we also know already that light can interact with electrons, and electrons can be lifted up from one state into a higher state by an incoming photon, and when electrons go down from a higher state onto a lower state, then we get light out of the atom. So this is called absorption, right? The photon comes in, the electron absorbs the energy and goes on a higher energy level. This can only happen if that incoming photon has exactly an energy h times nu that matches the difference between E2 and E1. Otherwise it would not be absorbed and just go through the atom. The opposite process, spontaneous emission, that happens by itself, and when the electron is up here on the E2 state for a certain time, that depends on the lifetime of the state, then it goes back down on the ground state and emits a photon that has the same wavelength like the photon that shot it up there in the first place. So this is absorption and spontaneous emission. That's basically what we saw in the hydrogen emission spectrum. Those lines, they came out of spontaneous emission. Now there is a third type of emission which is called stimulated emission, and the stimulated emission works in a way that the incoming photon sort of shakes the electron loose on the state E2 and makes it go down to E1, and the result is that we get 2 electrons out, right? We shoot 1 electron in, it encourages, it stimulates this electron on the higher energy state to recombine on the ground state and emit its energy as a photon. So this here can be used as a light amplification scheme like you find it in a laser, because we can make two photons out of one photon. And the intriguing aspect of stimulated emission is that the emitted photon has the same phase like the incoming stimulating photon. So the light amplification not only gives us two photons for one, but it also gives us photons where the waves are exactly in the same phase. Now it's obvious in order to make this happen, we need a population inversion. So that means we need more electrons on the state E2 than we have on the state E1 in a system. Because if we would have more electrons on E1, then absorption would be more likely than the stimulated emission. And then, of course, we could not get this amplification going because we would simply absorb the incoming photons but not create two for one. So how can we create a system with a population inversion for making a laser? Population inversion cannot be achieved with a two-state system. At least three states are required. The reason for this is that in a two-state system, the incoming photons will always find competition between absorption and stimulated emission. So as long as we have more electrons in the ground state than we have in the upper level, we will get more absorption, but as soon as we have the same number of electrons in the higher level state, then the stimulated emission will compete with the absorption, and so we can never go beyond a 50-50 population on the two states. But if we use a three-state system in which one of the states is metastable, this means it has a longer lifetime than the other states, then we can create a population inversion. This is shown here. We have three states, E1, E3 and E2, and E2 is the metastable one, which serves as the population inversion state. So the way this works is one uses a frequency of light that matches E1 to E3, and with that one pumps the electrons up into E3. So this is the pump light, or the pump laser in many cases. Once the electrons are up in E3, they recombine onto E2 under emission of some light. And on E2, they have a longer lifetime, so they start accumulating. So now we created a situation that is a population inversion relative to the E1 ground state, and we can get the amplification through stimulated emission, where photons matching the energy difference between E1 and E2 can be amplified. As an example for the principle that real life is usually a little bit more complicated than theory, let's discuss the helium neon laser. The helium neon laser is based on a thin glass tube that is filled with helium neon gas mixture, and at the ends are mirrors. One mirror is highly reflective, the other is partially transmitting light. The purpose of these mirrors is to bounce light forth and back a few times in that tube before it can exit as a laser beam, and the purpose is to encourage the stimulated emission. Also in that glass tube are two electrodes that are connected to a high voltage power supply. And the purpose of this setup is to accelerate ions and electrons that you find in a gas for natural reasons, because there's cosmic radiation. These electrons and ions get accelerated with the high voltage, and then they run into helium atoms, and these helium atoms, they get excited from their ground state, the 1s2, into an excited state, which is the 1s1 2s1, and the energy difference is just 20.61 electron volts relative to the ground state. So these helium atoms that are floating around in the gas now, these excited helium atoms, they have a problem. They cannot radiatively decay into their ground state because the selection rules would be violated. You see, L is the same everywhere, because we have S, S, and S, and so this electron cannot decay under emitting radiation, and so it sits up here and waits for something to happen. And what happens is that it collides with a neon atom, And this neon atom happens to have an excited state, it's 2p5 5s1, which has nearly the same energy difference relative to the ground state. And because of this, a resonance energy exchange can happen. And so this electron can go back down on the ground state while shooting up this electron here into the exciting state. And now we have an excited neon atom which has an electron on a metastable state up here. And that is basically creating our inversion population. And the lasing transition is now between this excited state of the neon atom and its 2p5 3p1 state. So after a while we have enough electrons up here, and then we can have stimulated emission. So this is the lasing emission. Once the electron has emitted its light, then it needs to go back down on the ground state that this process can be repeated, and it does that via the 2p5 3s1 stage under emission of some more light. And from this state it can only recombine with the ground state through collisions with the tube wall, since otherwise it would be violating the selection rules. Down here you see one of these helium neon lasers. This is that narrow glass tube, and the light is red because the lasing transition here is 632 nanometers. And this concludes chapter 3. Thanks for watching.